home portion. Let me read you the directions. Because believe it or not, people don't read directions. I know that's shocking to you, but it's true. Directions. You may use notes, textbook, and other electronic resources to help you with this quiz, but you may not ask for help from another individual or from Math Studio faculty. Okay, this is for you to do, right? If you can't do it, then that gives you some information about what you might need to study, all right? So please, if I don't want to be giving any people zeros the second, third week of the semester, all right? So I just wanted to read that to you. You can hand this in to me anytime between today and Friday. Just slip it under my door, and if you forget where my office is, it's North 420 if you want to write it on the top, North 420. And also make sure you have your name at the top. Lots of times people hand things in without their names on it, and I have no idea whose it is. So that might be a great thing to do right now, is make sure your name's at the top of the take-home quiz. Okay, don't forget Project 1 is also due on Friday, and that's that little green sheet up back, which I gave you about a week or so ago, right? And the other thing I wanted to mention is if you look at next week's, the homework that's due next week, you will see something called Test 1 Prep. Okay, Test 1 Prep. And Test 1 Prep is exactly what it says. It's optional. It's under the homework section. And it says Test 1 Prep. And Caitlin and I put, and I think it says optional after it. Test 1 Prep. And that it's totally optional. There are no points assigned to this for homework, and the due date is 9/27, which is the day of your first test. Okay, it's Friday. It's a week from Friday. Okay. So yesterday, Caitlin and I went through every single objective in the prerequisite chapter and every single objective in the chapter 1, because your test will be on chapters P and chapter 1. We went through every objective that we thought you needed to make sure you had some understanding on, and we made sure we had at least one question for every single objective in this test prep section. Okay, so and Friday or Monday next week, I'll talk to you a little bit about some study skills for the test. The other thing, if you haven't been curious and looked ahead a little bit, is these lecture notes, this packet that we handed out to you, not only have classes 6, 7, and 8 on it, but at the end, the very last bunch of pages has a study guide attached to it with more questions to study. Okay, so you have these questions, you have your study guide questions, and guess what else you have? You have chapter tests for each of these chapters, and you have chapter review questions. You have more questions than you could possibly do between now and 9/27, but there's plenty out there for you to practice. Okay, so what you need to do is identify the areas that you're having a little bit of difficulty with and start there. So you want to start with your chapter test and, hey, look, if you're bing, 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 you're getting through stuff, you don't have to worry about it. Don't worry about it. Don't study it. Just maybe make a note. Remember, you're allowed to bring in a page of notes, both sides. Okay. So we'll talk a little more about studying on Monday probably. So let's take a look at complex numbers. Right? Complex numbers is a new number set, or a number set that actually contains all real numbers. Okay, so you have this big set of numbers called the complex numbers. And inside this complex number set are all of our real numbers, which I denote that way, double stem R. Those are all your real numbers. So every single real number is also a complex number. So let's take a look at what a complex number is. But before we get there, we have to define this thing called I. Okay. Now, those of you who like history of math and wonder where stuff comes from, there were these competitions back in the 1600s. And in Italy, and people would solve equations. And remember, people were not as sophisticated as we are back then, in the sense of they didn't have the body of algebra available to them that we have become familiar with. So they would have these like competitions and people would solve equations, they'd win money, and this was like a great like activity in the Renaissance area. And there was this guy named Cardano, and he was trying to solve an equation, and he came up with this invention. That's exactly what it is. It's an invention. It's a definition. You will never feel intuitively anything about I. Okay? I is defined to be the square root of -1. We know that the square root of -1, that there's no real number in the world on that number line that represents the square root of -1, because there is no real number that satisfies this equation. So we created something called an imaginary unit. I is an imaginary unit, and its definition is the square root of -1. And what that helps us to do is it helps us to now write the square root of negative numbers. And the way we do that is we take the square root of -49 and we take our radical, and the first thing we do is we break -49 up into -1 times +49. And then we take our radical and we first apply it to the square root of -1, and then we apply it to the square root of 49. And we all know that the square root of 49 is the number 7, and the square root of -1 has just been defined to be this number I. So you can leave it like that, but multiplication doesn't matter. You could also write it as 7i. That's usually the preferred way. We usually put the constant factor in front of the I, but it doesn't matter if you write I times 7. So as you see, any type of square root of a negative number that happens to be perfect square, like as a positive number, is just going to be the square root of that number with an I attached to it. So in general, you can always write, you can go right from this step to this step, or square root of k times I. So whatever k is, you take its square root and you attach an I to it. Well, sometimes the number is not a perfect square, like the absolute value of the number is not a perfect square, and it's a little more work, but by now you've done a lot of work with simplifying radicals, so it's not too bad for you. We know the square root of -I is the square root of -1 is I, and the square root of 8, remember we just divided up into two factors where one of those factors makes you happy because it's a perfect square. Square root of 4 is 2, so we can rewrite this as 2 times I, and the square root of 2 can't be written any other way except for the square root of 2 because it's irrational. So square root of -I is this complex number. Okay? Square root of -49 is that complex number. And I square we define, and this will be useful in the work we do in a few minutes. I square is defined to be -1. It's a definition. So whenever you see I square, you can replace it with the number -1. So that's just some basic square roots using the imaginary unit I. Any questions on A or B here and how I got these two answers? Any questions yet, Tara? Absolutely not, because it's all multiplication. Okay, anything else? The order doesn't matter. Okay, so like probably like most people might write, well, I'll tell you in this particular one, there's a preference right here. Notice how I put the I out front of the radical symbol? And that's so that, you know, sometimes we can be sloppy and we don't necessarily stop where this radical is, like right over the 2, we might go like that, right? So you want to put the I in front so that it's really clear that it's not under the radical. All right, it's not under this radical. So that's probably the only time where there's kind of a preference to make it really clear that I is out front of that radical. But other than that, it doesn't matter, Tara. Okay. All right. That's the one time when I've seen stuff in books where they say there is a preference. Okay, so now complex numbers. You see here the complex numbers can be made up from real numbers and imaginary numbers. When you push them together, you get this form, a plus bi, where a and b are both real numbers. Okay, so you could have a number that looks like this, 2 plus 5i. We call 2 the real part. Oops, I must have moved this because the arrow's not going in the right direction. No. Oh, sorry, the 2 is the real part. That arrow should be going this way. I have to fix that on my lecture notes. And 5 is called the imaginary part. Now, as you can see, we can write every single real number. Here's the real number 5. Now, most of us are not going to go around writing 5 as 5 plus 0i, but we could. We could represent 5 in this form because our property that 0 times any number still holds. So 5 is equal to 5 plus 0, 9. So every single real number that you know and love can be written as a complex. Okay? So again, it's just like you could think of real numbers as all the GCC women students, and you could think of the imaginary numbers as all the GCC male students. And together, there's no intersection, right? One set has, if you try to ask for the intersection of these sets, they would be empty. But when you put them together, you would get all GCC students. And that's exactly how complex and real numbers work. Now, I know that there's some possibilities of overlap there, but I'm trying to stick with just, straightforward males and females, all right? So maybe in sociology we could talk about something else, but just for math, maybe I better come up with a different example next time. Okay, so every real number is also considered complex, but not vice versa. Just like every square is a rectangle. Every square is a rectangle, but not vice versa. Okay, so this is what we call complex numbers. And we can add them, subtract them, multiply, and divide them. So let's take a look at this. So here's a complex number, and I'm adding another complex number. Those parentheses are doing absolutely nothing except for saying, hey, here's a complex number, and here's another one. You can drop those parentheses and just write each of the terms that are there. Terms are separated by an addition and subtraction sign. So I have 4 terms. And we always know that in algebra, to simplify, we want to combine like terms. That's what the language means. So we see that we have 2 constant terms, 2 and 1, and that becomes the number 3. And then we have 2 other terms that are like. We have 3 i's and 5 i's. So we add the coefficients, 3 and 5, and that gives us 8 i's. Okay? And there's our complex number answer, 3 plus 8i. So you just put together the like parts. The only time you have to worry is when you have a subtraction problem of complex numbers. You can drop these first set of parentheses with no problem. But when you drop the second set, you have to remember that that subtraction applies to both the 1 and the 5i. So you have to subtract the 1 and you have to subtract the 5i. So put a little star right there above the subtraction of 5i, because that tends to be where people make their mistakes. So 2 take away 1, we can call the number 1, and then 3i take away 5i, 3 take away 5 is negative 2, the like part is called I. And there's our second complex number. Any questions on that? Squishing them together with adding and subtracting? Okay, the fun comes in, and I mean this, it really gets to be fun when you multiply these, because and really the fun begins here with E, but we'll go through D first. So here, this looks like a binomial. It's 2 terms right here, 1, 2. Here's a binomial times another binomial. So to multiply binomials, we use our famous FOIL, right? Our little technique of first term times first term, 2 times 1. Our outer term, 2 times 5i is 2 times 5 is 10i. My middle term is going to be like. So I can always get to add those together. So most of you write it right beside it horizontally. I'm just going to write it right underneath, so we add them. And then our final outer term is 3 times 5, which is 15. And then we have I times I, which is I squared. So we put the like pieces together, 2 and 13 i's and 15 I squared. And we sort of think we're done. But remember, we defined I squared to be equal to the number -1. So where you see an I squared, you can replace it with -1. So that means this thing called 15I squared really means 15 times -1. And now I have 13I here. And when I put these two guys together, I get -13. So I get -13 plus 13I. And that's my answer. That's my complex number. Because this becomes -15 now, and 2 minus 15 is -13. What did you have on your paper? Oh, okay. It's this right in here is times between these two right here, times. Okay, so that's a good question in case someone else did the same thing. Mary? Usually that's the form of every complex number is this, but if you wrote that as 13I minus 13, it's the same. Doesn't matter. This is just the conventional way to write a complex number, but these addition is commutative, so you could also write it like that. Anything else? Yeah, Adam? Yes. So for those of you who are curious, and it becomes a cycle. I equals the square root of -1. I square is considered to be -1. I cubed is -I, and which is negative square root of -1, and I to the 4th is +1. And then it starts all over again. I to the 5th, why does it start all over again? Because I to the 5th can be written as I to the 4th times I to the 1st, which is just 1 times I. So once you start all over, you just subtract 4 from the exponent, and then it's got to be one of those first 4 answers we have right here. I to any exponent has to be one of these 4 answers. Okay? But we won't use anything other than this, I square. But, okay. There's always curiosities out here. Let's take a look at this. I want to get a new piece of paper. So we have what? 2 plus 3I and 2 minus 3I, right? All right. So 2 plus 3I and 2 minus 3I, don't they look sort of the same? They're not a perfect square, though, because to be a perfect square, they'd either both have to be addition or they'd both have to be subtraction, right? So we called 2 plus 3I and 2 minus 3I. These are called conjugates of each other. Conjugates. Okay? And to make conjugates, everything looks the same, both terms, except for your operations. One is addition, one is subtraction. So if I asked you for the conjugate of this number, 15 minus 3I, what would its conjugate be? 15 plus 3I. You just change the operation to its inverse, either subtraction to addition or addition to subtraction. So something interesting happens with conjugates when you do your FOIL. 2 times 2 gives you 4. Your outer term is -6I. Your inner term is +6I. And when you add those together, what happens? Yeah, it becomes zippio, 0. And then 3I times a -3I becomes a -9I square. So this is what we get, 4 minus 9I square. But I replace I square with a -1. And when I multiply 9 times -1, I get a -9. And 4 minus a -9 becomes 4 plus 9. So notice I'm leaving it there. It's the sum of 2 perfect squares. I'll show you this in a minute in a little more detail. And of course, we would simplify that and call it 13 because we can put 4 and 9 together. Okay? So anytime you have conjugates, you can get to the answer really quickly if you recognize what we just did. And it's going to take practice. You're not going to be able to do this the first time you see it. For example, if I gave you this, 3 plus 5i times 3 minus 5i. Here's your answer. 9 plus 25, 34. Okay? But you're going to have to do this for a while till you get there, and that's okay. Let's try it again. 6 plus 7i times 6 minus 7i. 6 square, 7 square with a plus. Boom, you're done. Okay? But it takes a while. Just, I'll give you a little goal for yourself, a little aspirational goal. Yep. And it becomes a plus. Why does it become a plus? Because I squared is negative. And this positive, this addition times that subtraction will change it to a plus. All right. We just talked about conjugates. We'll skip that. So here's a helpful shortcut right here. We have one complex number times its conjugate. Can we go right to the answer without doing FOIL? What's the first term going to look like? A squared. What's the operation between them going to become? Plus what? B squared. Yep. So guess what? You now have the ability to factor the sum of two perfect squares. Just what you've been waiting for your whole life. So now, I know I'm being silly. Before, when you saw something like that and we were factoring with the real numbers, you'd say, no can do, it's prime. Now you can say, ooh, I can do that with complex numbers. X plus 2i minus 2i. Oh my God, cool. All right, but you don't need that. I just think it's kind of cool to see. All right, that's because I'm a nerd, right? All right, so anyway. So here's the one spot you got to be really careful of. The square root of negative 20 and the square root of negative 5 are not real numbers. They are complex numbers. The rules for radicals, those properties for exponents and radicals that we looked at, this property here, where you can put them under one roof, only applies to real numbers. So this is where some students make a little mistake. When you are asked to evaluate the product of two square roots where one or both are negative, you must do them individually. So this becomes the square root of negative 1 times the square root of 20 times the square root of negative 1 times the square root of 5. The square root of negative 1 is I. The square root of negative 1 over, so I'm just going to reorder them and put them like this because the order doesn't matter. So just so you can see what I'm doing, I'm just reordering. Okay. Square root of negative 1 times the square root of negative 1 is I times the square root of 20 times the square root of 5. Now the square root of 20 times the square root of 5 can be written as square root of 100, which is 10i squared. And I squared can be replaced with negative 1, which is negative 10. So the answer to this is negative 10. Okay. The mistake that some students make when they first see this is they forget that these are not real numbers and they try to apply this rule. So they do this. Oh, I can throw them under one radical sign. Oh, and get the square root of positive 100, which is 10. No. Okay. This property only applies to real numbers. So you've got to work these out individually. The answer to this is negative 10. You might. No, it isn't. No. No. The square root of 100. What does this symbol mean? What does this symbol mean? What is it asking for? the non-negative square root or the positive square root. This is the principal square root. When you see this, it's asking for the positive or 0. If this was a square root of 0, I just like to say positive square root, but technically it's non-negative. This answer is 10. To get the negative value, the negative 10 which you can square, that negative sign has to be outside of the positive. That's your negative 10. Okay? But anytime you see this symbol, it's looking for the non-negative square root only. That came up in the last class too. So keep those questions coming and those observations, because if it's a little confusing, it's good to get it out there. Okay? All right. Now, let's take a look at quadratic equations, because this is where we use these complex numbers. Caitlin and I wanted to just have a little recall here with some language that maybe you're not familiar with, which is this language right here that I'm highlighting. I think everyone could write down, if I asked you on your exam next week, give me an example of a linear equation. I think you could write down a linear equation. And it's just something you do without thought. And if I asked you for an example of a quadratic, I hope you could show me a quadratic. But the term that we use, a similar term or an equivalent term, is first degree and second degree. And the degree part may not be the most familiar to some of you. Is anybody, from looking at this, can you tell why we might call a linear equation a first degree and a quadratic equation a second degree? Haley? Yeah? Yep, you see that this is a squared term, right? And do you see anything higher than a squared term anywhere in that equation? Nope. And do you see anything higher than a squared term here? No. So second degree says the biggest exponent you're going to see anywhere across, if you're in one variable, is a 2. That's where the second, oops, that's a little wide for, let's see if I can get it skinnier. Oh, I got to erase it first. So the second degree here says that the highest exponent you see in that equation, as Haley pointed out, is 2. And even though we don't see it on this particular equation, a linear, you see that it's a 1. And that tells you something, folks. It tells you the most number of elements in the solution set. The solution set for a second degree equation can have 2 answers in it. That's the most it can have. It could have one real number, or it could have no real numbers. It could be empty. For the linear equation, the most number of solutions you can have in the solution set is just 1. But you may have a linear equation with no solutions. So you either have 1 or empty set. With a quadratic, you could have 2, 1, or an empty set, if we're dealing with real numbers. Once we bring in the complex numbers, we can have 2 answers or 1. Well, actually, always 2 with complex. If you have one complex answer, you'll always get a second one. It's called its conjugate. So in general, a quadratic equation is a second degree equation where we can write in this form, the general form, and the only condition we have on this is that a cannot be 0. Because if a is 0, we now have a linear equation, right? The ax squared would go away and it would be a linear equation. So this is what we call the general form of a quadratic equation, or the standard form. That's just another way to write it. Okay. Well, we've already been working with quadratic equations in this class without calling them that. And where we've been doing that is, I'll show you, when you've been asked things like this. So you've been doing this for homework. Okay, and you've been asked to find the excluded value, right? Of values. And how have you done that? What process have you gone through to find the excluded values for a rational expression or an algebraic fraction? What have you done? Tara? Factored. Okay, so what did you factor? okay? So you're looking at the expression in the denominator. It is not an equation. It's an expression. So this is called a trinomial. Quadratic refers to, you could call it a quadratic trinomial. You could call it a second degree trinomial, but it's not an equation. And then what process do we go through once we factor that to get the excluded value? What process have we gone through? Find out where it equals 0. So you set that trinomial equal to 0, which makes it an equation, quadratic equation. And then you've been factoring it and using this idea that when you multiply two things and you get 0, one of them 0 or the other one 0. So you have already seen how to solve quadratic equations by factoring, because you've been doing it all along in section P6. So we know that if we set that factor equal to 0, our answer is x equals 5. And we know if we set this equal to 0, if this started off as an equation, it would be x equals -2. So in finding our excluded values, you've already had a little bit of practice on how to solve quadratic equations. So let's scoot over to the part, I'm going to skip one part of your lecture notes, but I'll come back. Let's scoot over to number 12 in your lecture notes. Number 12. And what page is that on, number 12? Page 10. Okay, so imagine, folks, take all the zeros off of these. Take all the equal zeros off, all three of them. And imagine those were denominators where you were trying to find the excluded values. What you would do is you would set those denominators equal to 0 and you would factor, right? So let's factor them. Which one can you factor like the quickest and the easiest? I'm just curious. Which one? Which one can you like look at and boom, you know how to factor it real quick? So some say A, some say C. Anybody say B? No? All right. What about C? How can you factor that really quick? What category does C fall under? There's a name for it. No, perfect squares would have 3 terms, but there is a square in there somewhere. Tara? The difference of squares, right? Because you got a subtraction. X squared is a perfect square, and what about 49? Another one. So this can be factored fairly quickly. X, 7, 7, and then because it's a difference, plus, minus. That way you won't forget. See that little 2 there as an exponent? That tells you 2 answers. I got 2 answers in my solution set, plus and minus 7. Nope. But on your homework, I'll get to that. -7, x minus 7 equals 0, x equals plus 7. And in your math, my math lab, I don't care whether you write 7 or -7 first, but when you're writing a set in my math lab, they want it in ascending order. So you always write your negative number first and then your positive number. Okay, for my math lab. Can you not play with that, please? What about the first one? Now, someone just said, I think it was Adam said, that's easy to factor to him, but that's the kind you get real stuck on, a lot of you, because you forget your very first factoring technique. And in fact, I encouraged my 106 students to write what on their palm? Lenny and Beth, do you remember? Close. Nope. Nope, close. GCF, right. I said, you know, maybe I'll get a tattoo, GCF. And I said, put it on your palm. You can take it into the test. It's fine. Because that's the one you forget. You're so used to like looking at these kind, you want a constant there. Okay? But when you have the quadratic term, listen to my language, the quadratic term and the linear term, you'll always have the base, which is the variable, as common. They both have an x in them. So you can factor this like this. And lo and behold, you set each factor equal to 0. No work to do with the first factor. It's x. So you set x equal to 0. That's one solution. and you set the other factor equal to 0, and you get x equals -1. So this solution set has -1 and 0. Okay? Again, 2 answers. Notice your exponent, 2. Now, Mary asked a question, I believe, way back a week ago or so. I think it was Mary, said, can I divide both sides by x? And if you do that, you divide this by x, you get x. You divide this by x, you get 1, and you're just left with this equation. So what happens when you divide by x is you're losing one of your possible solutions. And in this case, that solution happens to equal 0, so it's a big taboo because you're dividing both sides by 0, which you're not allowed to do. So you never want to divide a quadratic equation by a variable, by x, or whatever the variable in common happens to be. You want to factor it out, set that factor equal to 0, because you'll lose one of your answers. You should always be on the outlook for 2 possible answers as a maximum. Now, what about this middle one? How are we going to factor that? Well, you look at your last term, 24, and you say, what factors of 24 add up to 11? So what factors of 24 add up to 11? 8 and 3, right? And so you set up your 2 parentheses. You know both of your signs are addition, x and x, 8 and 3, and voila, you set each factor equal to 0, and life is good. You have your 2 answers. Now be careful when you write this in my math lab. Okay? What is your ascending order? Which is the smaller of the 2 numbers? -8. So you write -8 first and -3 second. Okie doke? So you've done those. No problem, right? You know how to factor. Let's come back now to, I think it's 10 right here. We've also done these. Well, we've done some of these. We've done A as a class. And when we were looking at A, I sort of gave you a little preview, and I said, this is going to be the kind of equation where you're going to forget something. And I told you one way to do it where you'll never forget it. And then we looked at the idea that the square root of a variable squared is absolute value. And that helps save some of us, okay? So there's 2 ways to do this kind of equation. Notice, these equations differ than the ones I just looked at. It only has your quadratic term and now your constant. That's it. There's no middle term here. So these can be done fairly rapidly as long as you don't forget what? How many answers? 2. See that 2 there? See that 2 there? Because what do people do? They say, oh, I know how to do that. I just put the square root over it and I get C is 3. Fabulous. You only got half the answers. Okay? When you undo a square root by taking the square root of z squared and the square root of 9, now the square root of 9 is 3 because I'm asking for the positive square root. But now this side we have a variable here. The square root of z squared is not z. It is, nope, absolute value of z. Okay? Because z could be a positive 3 or a negative 3. Then once you get here, you say, oh yeah, that's z inside there to be a 3 when it comes out. Z could be a 3 or z could be a negative 3. Voila, I'm done. Okay? Now one of my students in my 840 class said, Linda, can I just skip all this stuff here and just put z as plus or minus 3? Golden, I said, as long as you remember that, you're golden. But I said, I would bet my life, and I still would with this class. So if this, happens, I guess you have the right to bury me. But I would bet my life that if I give you an equation like this on the test, and you either don't use the second method we're going to discuss, or you skip that, I guarantee that not 100% of you will get z plus or minus 5. Guarantee it. I have almost 33 years of experience working with students. They'll just put, there will be one person in this class who will say z equals 5. So I am trying to give you the golden ticket to full credit. You can either use it or not, or abuse it. It's up to you, okay? Now, what's the other approach we can do here? Z squared equals 9, other than square root in both sides, which is called extraction of roots, if you want to know the name of that technique. What else can I do with this? What did I do with these other equations in number 12? What were they all set equal to? 0. So let's try that. If I set this equation equal to 0, can I easily factor that one? Yeah, it's difference of perfect squares again. Then you're guaranteed again, here's another guarantee for you. You won't forget that it has 2 answers when you solve that. So it's up to you. You can either take my advice or not. I don't really care. It's your life. It's your grade, right? No, I do care. All right. Second one, x squared equals negative 20. Yep, no. Because the original equation, Mel, looks like this. And I'm going to subtract 9 from both sides so I can set it equal to 0. Okay? Okay. Next one, x squared equals negative 25. If I use my square root method, I get the absolute value of x on this side, and I get 5i on that side. So what could go inside that absolute value? X could either be positive 5i, or x could be negative 5i. Works the same way as it does when your equation is equal to a real number, positive or negative. Okay. Now, why did I show you all that stuff with the conjugates? Because I wanted you to be able to factor this if you set that equation equal to 0. So the second technique here is to set the equation equal to 0 and factor. Well, you can factor it now. When you add 25 to both sides, you get this equation. Now you have the sum of perfect squares, which with the real number system you couldn't factor, but now you can factor. You can say, oh, x and x, 5i, plus or minus, they're conjugates of each other. And now you have 2 factors you set equal to 0, and you see your answers are x equals plus and minus 5i. Again, you'll get both answers. All right? So these equations that have a square on one side and a constant on the other side, you have 2 methods you can use. Actually, you'll have 3 in a minute. You can also use the quadratic formula if you like. Now C, yep.
So when you did x squared plus 25 equals 0, why is the second factor negative if it's plus 25?
Because we just did, remember when we just did FOIL with these a minute ago? You probably don't remember, Shane. When we did this, we got negative 25i squared. And remember we said I squared was negative 1, so that made it plus 25. That was sort of the cool result of that. So that when we get something like this now, we can write it like this. Before that, we didn't know how to do that. Like in Math 106, we couldn't have done that. So this one creates problems for students. And I'll show you the 2 reasons why it creates problems. The first problem is because, see right here on A, we got a 1 in front of the z squared and we got a 1 in front of the x squared. So there's nothing to do there. So the first thing you need to do here is you need to undo the multiplication of negative 2. And how do you undo the multiplication of negative 2? You divide by what? Negative 2. So you want to divide both sides by negative 2 because you want to get a 1 out in front of that square term. Okay, so you get x minus 7 squared is now equal to 10. And let me show you what most of you will do. Oh, I don't actually know if I can put an adjective on this. Okay, so what is your tendency when you see something like that squared versus your tendency here when you just see a single thing squared, you throw the square root symbol over it. No problem. But when you see something like this squared, what do you tend to do? You think? Maybe not. Maybe I'm misreading. Oh no, I hope not. I hope you don't square both terms and add them. I'll be very sad. This is not the exponent property with this applies to that and that is not. What does this mean? X minus 7 squared. If you did it out the long way, what does it mean? No! X minus 7 times X minus 7 equals 10. And when you FOIL it, what do you get? You do not get X squared plus 49, Shane. You get X squared minus 14X plus 49 is 10. You'll subtract 10 from both sides, and you'll get that. And then you'll say, now what? Can't factor that. So if you do it that way, you need the quadratic equation. Okay? But there is a way to do this where you don't need the quadratic equation, and it's doing exactly what you did with these other two. This is just something squared, just like z squared and x squared. Train your eyes. Okay? Remember we used that little substitution? You could let big capital A, if you want, pick any letter or symbol, equal x minus 7. So now this equation looks like this. A squared equals 10. That's what it looks like. And now what do? You say, okay, I'm going to square root both sides, and I'm going to get A equals plus or minus the square root of 10. Just like that. And you're almost done, except for the original equation was in terms of x, not A. So where you see A, you replace it with x minus 7, which is what it was equal to. And now you solve for x by adding 7 to both sides. And you get x equals 7 plus the square root of 10. And x equals 7 minus the square root of 10. Two answers, they're conjugates of each other. Anytime you have a complex number for an answer to a quadratic equation, its conjugate comes along for free. Always, always, always. So if I told you this was the answer to a quadratic equation and I asked you what the other answer would look like without telling you, you can say to me, I know it's its conjugate. 7, take away the square root of 10. They are always buddies. They pair up. They're like frick and frack. They go everywhere together. Peanut butter and jelly. Okay? Conjugates are in pairs. Whatever pairing you have in your mind. All right? Hold on. 39. Well, Christian, I was showing you a method I wouldn't go through here. Like, I'm saying that most students would square this out. And you can't do this by factoring. There are no factors of 39 that add to 14, so you'd have to use your quadratic equation. Instead, what I'm trying to do is get you to see that this equation, could you shut the door, Mary, thanks? Looks like this equation and this equation. You have something square equals a constant. So all I did to help you see that is I just replaced this with the big capital A, just so you could see that. Okay, I'm just saying let A equal x minus 7. And then if I gave you this to solve, you would square root both sides and get plus or minus square root of 10. And then you scoot it back in. All right, so quadratic equation, anybody remember that? It's a song. Yes, we have a song. And I didn't have time to get my little song going. So you're going to have to put up with me without the melody. So the song for remembering the quadratic equation goes to this song. The melody goes to this song. Does anybody recognize this? All around the mulberry bush, the monkey chased the weasel. The monkey thought 'twas all in fun. Up goes the weasel. How's that melody go? Da na 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 na. Do you know it? Na 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 na. You know that melody? Is it fairly familiar? All right. So now, to remember the quadratic equation, I once made the mistake of wearing one of my colleagues, this was way back in the 80s, gave me a t-shirt because I said to my students, you have to memorize this. You're not going to be able to take any notes in. It's time to memorize the quadratic equation. You're going to have it on your quiz tomorrow. So he gave me his t-shirt, which had the quadratic equation on it, and I put it under my shirt. So now instead, I sing it to you, which is almost as bad because I don't have the greatest voice. but I'll do it once, and here's the words, and then we're going to try it together. Okay, so x equals negative b plus or minus the square root of b squared minus 4ac. I can't get up there anymore. All over 2a. I didn't make it. Maybe some of you will make it. Ready? Together. 1, 2, 3. X equals negative b plus or minus the square root of b squared minus 4ac. Very good. Very good. You got there. All right. Now, students have always complained to me about this because they said I couldn't get it out of my head. That's great, because now you'll never forget the quadratic equation. You already forgot it? All right, so what do you need for the quadratic equation? You need to be able to identify the a, b, and c terms, right? So what are a, b, and c in this first equation here? Let's take a look. A is the coefficient of your x squared term. What is it here? 1. B is the coefficient of your x term called your linear term. What is it? Negative 6, right? And C is negative 7. Okay. And it's a plug-in from there. B, we got to do something to before we identify A, B, and C. What do we have to do to this equation? Let's take a look. Here's the quadratic equation right here. We missed all the steps called completing the square to get down to here. But x equals, but what form is this quadratic equation in? That this quadratic equation and this, well, this is the only one that's not in that form. Has to be set equal to 0 to use the quadratic equation. Now it's totally up to you folks. You can subtract the 20x from both sides and add 6 to both sides. You can do it like that. Or you can subtract 5x squared from both sides in one step. And it doesn't matter. Your answers will be the same. One will be, you'll see it, well, anyway, they'll be the same. So in this case, A equals B, C equals, B equals, I'm trying to go too fast because I looked at the clock. All right. A equals 5. B equals negative 20 and C equals 6. Over here, A equals negative 5, B equals positive 20, and C equals negative 6. So it just depends on which one you want to do. So let's pick one. Do you want to do one together before you go off into your merry life and have lunch? Is there one you'd like to see done? Which one? C. Let's take a look at C. Let's identify A. What is A here? What is B? And C is 9. All right. Guess what? That's a perfect square. That's the one time you have one answer. That can be factored. I wouldn't use the quadratic equation on that. If I can factor it pretty quickly, I wouldn't do it. But let's do it and see how we get this answer. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. X equals negative 12 plus or minus 12 square is good. You know your 12's tables. 16 times 9. What is it? That's how I get just one answer. When I have 0 underneath, right? Negative 12 plus or minus the square root of 0 is 0. So guess what? I'm only going to get one answer because when I add or subtract 0, it doesn't change. Negative 12/8, and lo and behold, that reduces to negative 3/2. Okay. Hey, see you on Friday.